earlier we talked about the reflection of transverse waves from a denser medium and a rarer medium. Now let's talk about the reflection of longitudinal waves. Okay, let's suppose we have a longitudinal wave, for an example sound, which is moving from a rarer medium to a denser medium. Okay, so as an example of a denser medium, let's consider this rigid wall. So what will happen? Okay, so now let's suppose a compression. So longitudinal waves, they consist of alternate compressions and rarefactions. So let's suppose compressions, a compression travels, okay, towards this rigid wall, hits that rigid wall. So what will happen? Whether it will get reflected as a compression or as a rarefaction. So the answer is it will get reflected as a compression. Okay. So to understand why will it get reflected as a compression, let's imagine what happens in case of a compression. So different particles, various particles of medium, they collide. Okay, so density of that region increases, and that is the compression. Okay, so that is compression, right? So n number of particles, a large number of particles, they are packed in very small volume. So this is a compression. Okay, so now see, there are a lot of particles. Okay, these are all suppose particles of the rarer medium, and they hit this rigid wall. Okay, they hit this rigid wall. Okay, so what will happen? These particles, they will exert some force on the wall. Wall will also exert equal and opposite force. Okay, but wall is immovable. Wall will not move, right? So particles, they bounce back and they collide on the other particles. Because it's a compression, the density of particles in that region is more, right? So there are large number of particles. Okay, so these particles, they collide onto the wall, they get reflected back. Okay, they bounce back. Wall does not move, wall remains there itself. Okay, so particles, they collide on the other particles, right? So now again, so density of that medium does not change, you can see it doesn't decrease. Okay, so the compression hits the denser medium, it gets reflected. I'm sorry, it gets reflected as a compression. Now imagine what will happen when rarefaction hits the rigid wall. So in that case, rarefaction is less number of particles. Okay, so less number of particles hit rigid wall. So these particles are already going away from each other, right? So these particles, they are hitting the wall, other particles are going away, and these particles, they get reflected from the wall. Okay, so again, now the density of the medium, it is not changing, right? So if density was large, the density will remain large. Okay, density was more, it will remain more. If it was less, it will remain less. So compression gets reflected as a compression, okay, when wave travels from a rarer medium to a denser medium, and rarefaction gets reflected as a rarefaction. Okay, so this is a rigid wall, but instead of rigid wall, you can consider air and water. Okay, so particles of air, they are not capable enough to move particles of water, you can say, because particles of water, they are closely packed, so it is very heavy, right? So when the compression hits, compression which is traveling through air, it hits the surface of water, again it will get reflected as a compression. And if rarefaction gets incident on the surface of water, it will get reflected as a rarefaction. So in case of transverse waves, we studied that if crust gets incident, crust travels through a rarer medium, it strikes a denser medium, it gets reflected back as a drop. Okay, so there is phase shift of pi. So how much would be phase shift in case of longitudinal waves or longitudinal waves? It will be Zero. There is no phase shift, right? Because compression gets reflected as a compression and rarefaction gets reflected as a rarefaction. So there is no phase shift. Okay. So then let's talk about wave which is traveling from a denser medium to a rarer medium, right? A wave which is traveling from denser medium to a rarer medium. Okay. So now see what happens. So for an example, you can consider this medium is solid, okay, and this is air, okay. So see now what happens here. So when compression comes, okay, so now what is happening? The particles of this medium, denser medium, they are vibrating, okay. So here you have particles of rarer medium. So particles of denser medium are closely packed, and now when a compression or rarefaction comes, what will happen? It has it has got space to expand into the rarer medium. Okay, it has got space to expand into the rarer medium. Okay, so see when compression comes, what will happen? These particles they will exert a force on particles of rarer medium. They will also exert a force. But now see now what's happening here? These particles of rarer medium they are pushed away and this compression travels into the rarer medium. Why? Because there are other particles which are coming in from backside. They are pushing these particles further. Okay, so this compression it travels into the rarer medium, right? In case of rarefaction also the same thing happens. Okay, so what will happen? The rarefaction it will travel into the rarer medium. So particles are moving apart. Okay, so here there are very less number of particles. So these particles, so imagine particles here, n number of particles, they are moving apart. Some particles are moving in this direction, some are moving in the other direction in case of rarefaction. So these particles which are moving in forward direction, they can move inside this rarer medium. Okay, so they can separate, they can still get separated. Okay, so now what happens? So compression or rarefaction travels into the rarer medium. Okay. So now if compression travels into the rarer medium, what will happen? What follows the compression? Rarefaction follows, right? So the compression will get reflected as a rarefaction. Okay. Or you can say rarefaction it travels in a rarer medium. And what follows the rarefaction? Compression follows rarefaction. Okay, so rarefaction travels into the rarer medium, and the next thing which is coming, that's the compression, it gets reflected. So when a wave travels from a denser medium to a rarer medium, there is phase shift of pi now. Okay, so when a wave, which wave? Longitudinal wave travels from a denser medium to a rarer medium. So since compression gets reflected as a rarefaction, rarefaction gets reflected as a compression, there is phase shift of pi in this case. All right. Okay, so uh, this is reflection of longitudinal waves. Okay, and after that, let's talk about vibration of air columns. So let's discuss vibration of air columns. Now what is this thing? So you have cylindrical pipes. Okay, you have a cylindrical pipe and you take a tuning fork. So consider this pipe. This is a cylindrical pipe. Okay. Okay, you have a pipe like this. You have a cylindrical pipe and suppose it is closed at one end. Okay. So you can imagine, for an example, any container. okay, any container from your kitchen, right? Any steel container, okay, a cylindrical container. And if you open the lid of that container, so what remains is a cylindrical pipe and it is closed at one end. So now we are going to study vibrations of air columns. So what is air column? The air inside the cylindrical pipe, okay, which is closed at one end. So we'll see vibration of air columns in case of a closed pipe. Okay, so the pipe which is closed at one end and the pipe which is open at both ends. Okay, so let's consider a pipe which is closed at one end. So let's suppose this is the pipe, it is closed at one end. So now you take a tuning fork. So this is a tuning fork. You take it, you hammer it on a rubber pad or on your hand and you keep it over here. So what will happen? The prongs of the tuning fork, they will vibrate like this. Okay. So these prongs, they will vibrate like this. So they will push the air, right? So they will be bend inwards and outwards. So because of vibrations of these prongs of tuning fork, what will happen here? Compressions and rarefactions will get produced. These compressions and rarefactions, they travel, okay? They travel in this medium and they get reflected back. They get reflected back from this end, from the rigid end. Okay. So now, because of compressions and rarefactions, or you can say the longitudinal wave, which is traveling in this direction, and a wave which gets reflected like this, what will happen? These two waves overlap onto each other, and a stationary wave is formed. Okay, so longitudinal stationary wave is formed. Okay, so now what will happen at this end, which is closed? So this end is closed. So therefore, now particles, they don't have much space to vibrate. Okay, so particles here, they will not be able to vibrate, right? So therefore, compression is produced here. Okay, and on this end, particles have space to vibrate. Okay, particles can move, right, towards each other, away from each other. So they have space to vibrate. So therefore, what happens is the rarefaction gets produced here. Okay, or in other words, you can say here the pressure would be more because of end is closed. Okay, so it keeps on exerting a force, right? So pressure is more here at this end, pressure is less at the other end. So because of difference in pressure, compression is produced at this end, okay, and rarefaction is produced at the other end. All right. Okay, so I will explain it once again. So see what happens. Compressions and rarefactions are produced, okay, due to vibrations of tuning fork, okay, and these compressions and rarefactions, they travel through this medium, right? So now when they arrive at this end, this is the closed end, okay, this is closed end, they get reflected back from there. Okay, so now what will happen, since this is closed end, it can exert force, okay, large force, right? And here the particles are able to vibrate. Okay, so this is free end, we can say. This is closed end. So at free end, particles can vibrate with maximum amplitude, and at the closed end, there is no much space for vibration of particles. And therefore, at this end, okay, so see, at this end, there will be always a compression, and at the other end, there will be always a rarefaction. Always a rarefaction will be there. Okay, the reason is this is closed end, this is free end. Okay, so particles can vibrate here with maximum amplitude, and because this end is closed, so in case of stationary wave now, particles won't be able to vibrate much, right? So therefore, now since particles cannot vibrate here, we say that this is a node. and this is an antinode. Okay, so we draw it symbolically. So this is symbolic picture. Okay, this is symbolic picture. So see, we draw it like this. Okay, so this is a node. So we compare this thing, vibration of air column, with vibration of string. So if you compare with that, so this is a string. So particles at the node, they cannot vibrate much. Particles at the antinode, they can vibrate, right? So what is produced at this end? An antinode is produced. Antinode is produced. What is produced at this end? A node is produced. So we draw it like this. Okay, so this is the node, this is antinode. Okay, so now how much would be this length? So we know that in case of vibration of string, one loop is equal to what? Lambda by 2. Length of one loop is lambda by 2. So this is not even one loop. This is half of the loop. Okay, so distance between a node and an antinode. This is half of the loop. So what happens? This length is equal to what? It is equal to lambda by 4. This length will be equal to lambda by 4. Okay, is it clear? So now this is fundamental mode of vibration of a pipe which is closed at one end. Okay, so this is a closed pipe. Right, this is a closed pipe, and in case of fundamental mode, let me shift this further. In case of the fundamental mode, what can I say? That L is equal to lambda by 4, which implies that lambda is equal to 4 times L. Okay, 4 times L. And then we know speed of waves is equal to n lambda, right? And therefore, I can say that n, the frequency of fundamental mode, is v upon lambda, that is v divided by 4L. So this is fundamental frequency of vibration of air column in a closed pipe. Okay, this is fundamental frequency. Right? This is fundamental frequency. Okay, n is equal to v divided by 4L. Okay, so this is called as the fundamental mode of vibration. Now in fundamental mode, what happens? Half of the loop is produced. Okay, then let's consider the similar pipe once again of the same length. Okay, let's consider pipe of the same length, and let's consider second harmonic. So fundamental mode is called as first harmonic. What is second harmonic? First frequency higher than the first harmonic. Okay, so let's consider second mode of vibration. Second mode of vibration. Now I will not draw an air column. Okay, so we'll just visualize it. Like this. Okay, so this is node. So this is symbolic representation. Okay, this is not how literally it looks like. It looks like this. There will be a compression on this end, a rarefaction on this end, right? So now if you increase the number of mode, okay, if you go to second mode of vibration, that means you take another tuning fork of higher frequency, okay, and you make this air column vibrate. Okay, so what can be the second mode? What can be the next frequency that can be resonant with the vibrations of tuning fork? Okay, so that is second mode of vibration, or you can call it second harmonic. So in case of first mode, what happens? A node is produced here, an antinode is produced here. So same thing will happen here also. At this end, there will be always a node. At free end, there will be always an antinode produced. Okay, an antinode is produced there. So what can happen in between? So one loop can get formed, one loop can get formed. So actually loops are not forming. There is no string. What is this? These are compressions and rarefactions. We are visualizing them as a vibration of string. Okay. So this is a node. This is an antinode. This is a node. Okay. Another antinode. So how much is this distance? We know this distance is equal to lambda by 2. This distance is lambda by 4. Okay. So for second mode of vibration, we can say that L is equal to lambda by 2 plus lambda by 4. It is 3 times lambda by 4. And let's call this lambda 2. Okay, the wavelength of second mode is suppose lambda by 2. And therefore we can say N2 is V upon lambda 2. So you can find out lambda 2. I'm sorry. You can find out lambda 2 from here. So lambda 2 will be equal to what? 4L upon 3. Okay. Take 4 on that side, 3 on other side. So it is 4L divided by 3. So what do you get? You get N2 equals to V divided by 4L divided by 3. So the 3 is in denominator of denominator. So it goes to the numerator. Right? So how much is the frequency? N2 is equal to 3 times of V upon 4L. That is, it is equal to 3 times the fundamental frequency of vibration. So N2 is equal to 3 times of N. Similarly, we can take third mode of vibration. Okay, so for the case of third mode, this is the pipe. Okay, the length is same, right? So now what will happen? So frequency of this mode would be more, right? So always a node is produced at this end, which is closed end, and an antinode is produced here. Okay, so in between here, one loop was formed. Now two loops will be formed. Okay, now what will happen? Two loops will get formed. Okay, so again, let's remember it's not a string. Okay, this is just visualization. Okay, so it will look something like this, right? This is a node, antinode, node, antinode, node, and an antinode. So this is lambda by 4. This is lambda by 2. This is lambda by 2. Or you can say this is this much length. Okay, a compressed, sorry, crust and trough, right? This much distance is equal to what? This is equal to lambda. So this length is lambda plus lambda by 4. How much is vibrating length? Sorry. How much is vibrating length in terms of lambda? So L is the length of this pipe and it will be equal to what? Now lambda plus lambda by 4. So it is 5 lambda by 4. This is third mode of vibration. Okay, this is third mode of vibration. So here you can say that lambda 3 is equal to 4L divided by 5 and therefore N3 is N3, it's equal to V upon lambda 3, that is V divided by 4L divided by 5. The 5 goes to the numerator. So N3 is equal to 5 times of V upon 4L, right? Or you can say it is equal to 5 times of N. Okay, it is equal to 5 times of the fundamental frequency. Frequency of third mode. Okay, frequency of third mode. This is fifth harmonic. Okay, and this is frequency of p mode of vibration. It is 2p minus 1 multiplied by n, 2p minus 1 multiplied by fundamental frequency. So it is 2p minus 1th harmonic. So see, second mode of vibration will have frequency 3 times the fundamental frequency. Okay. Third mode of vibration will have frequency 5 times the fundamental frequency. That means the frequency of second mode of vibration is equal to what? 3 times n. Okay, it is third harmonic. Okay. So now see, when you move from first mode to second mode, you go directly from first harmonic to third harmonic. Okay. So second harmonic is not present there, right? Second harmonic is not present. When you go from second mode to third mode, you jump to the fifth harmonic. That means you jump from third harmonic to fifth harmonic. So fourth harmonic is not present. Okay. So that means in case of vibration of in case of vibration of in case of vibration of a pipe closed at one end, only odd harmonics are present, even harmonics are not present. Only odd harmonics are present. Okay. Even harmonics are not present. Now let's talk about overtones. So see, okay. So frequency of second mode of vibration is the first overtone. Frequency of third mode of vibration is the second overtone. So what is an overtone? Overtone is first overtone is first frequency higher than the fundamental frequency. Second overtone is second frequency higher than the fundamental frequency. Right? So see, what is first overtone? Frequency of first overtone here, it is equal to third harmonic. Okay. Frequency of second mode of vibration is called as first overtone, and it is equal to what? Third harmonic. Harmonic means multiple only. Okay. Then frequency of third mode of vibration. So this is third frequency, right? That means it is actually second frequency higher than fundamental frequency. Okay. So it is equal to 5 times n, right? So this is second overtone. So second overtone is equal to 5 times n. What will be third overtone? Third overtone will be 7 times n. Okay. So that means if you take pth overtone is equal to 2p plus 1 times the fundamental frequency. Okay. Pth overtone is equal to 2p plus 1 times the fundamental frequency. Good. So this is closed pipe. Now let's talk about an open pipe. Okay. So let's talk about vibration of air column in an open pipe. So this pipe is open at both ends. Okay. So let's consider an open pipe. This is the open pipe. So what will happen now? So if you take a tuning fork, okay, you hammer it on rubber pad, you keep it over here, you keep it over here, So it will set vibrations in the air column, okay, of this pipe. So now see, once again we can say that compressions and rarefactions are produced, they reach the other end, okay, and they get reflected back, right? So both ends now they are open. That means there is maximum freedom for the vibration of air particles. Okay. So since there is maximum freedom at this end as well as this end, what will happen? An antinode is produced at both of these ends. Okay, an antinode gets produced at both of these ends. Okay, so this is the fundamental mode of vibration. An antinode will get produced here, an antinode will get produced here, and in between those two antinodes, a node will get produced in the middle of the pipe, right? This is an antinode, and a node. Okay, so pipe will vibrate like this. So then, okay, then how much would be the frequency of this fundamental mode? So for fundamental mode, in case of open pipe now, how much is this length? This length is suppose L. In terms of lambda, so this is lambda by 4, this is lambda by 4. That means it is lambda by 2. Okay, the total length is lambda by 2. So L is equal to lambda by 2. That means lambda equals to 2L. Okay, so the frequency of fundamental mode, frequency of fundamental mode will be how much? So N is equal to V upon lambda, that is V upon 2L, right? Frequency of fundamental mode is V divided by 2L. Now if you compare this with the closed pipe of same length, how much is this frequency? This frequency is 2 times. Okay, this frequency is 2 times the frequency of fundamental mode of a closed pipe, right? It is V upon 4L, this is V upon 2L. Okay, so the frequency of open pipe, the fundamental frequency of open pipe will be twice as much the fundamental frequency of a closed pipe, okay, of the same length. Got it? How about the second mode now? So what will happen in case of second mode? So this is suppose the second mode. Okay. So let's suppose this pipe vibrates in second, sorry. So let's suppose this pipe vibrates in the second mode. So what will happen now? See, an antinode gets produced here, an antinode gets produced here. So in case of first mode, one node was produced in between. Now a loop will get formed. Okay, two nodes will get formed in between. So it will vibrate like this. Okay, this is an antinode, node, antinode, node, antinode. Okay, so how much would be frequency of second mode? So frequency of second mode, let's find out the relation between length and wavelength first. Okay, so length of the pipe for second mode, L is equal to this much length is lambda by 2. Okay, as we discussed uh, in this first case. Okay, fundamental mode, this much length is lambda by 2. Okay, so lambda by 2 plus lambda by 2 is 2 lambda. So this is equal to, sorry, lambda by 2 plus lambda by 2 is lambda, not 2 lambda. Okay, so L is equal to lambda. And then we know V equals to n lambda. So n is equal to V upon lambda. That means V upon L. Okay, So this is second mode. So let's put suffix 2 there. Okay. So N2 is equal to V upon L. That means N2 is equal to 2 times the frequency of fundamental mode. Okay. That was V upon 2L. This is V upon L. It's 2 times the frequency of fundamental mode. Okay. So N2 is second harmonic here. Second multiple of fundamental frequency. Second multiple means 2 times the fundamental frequency. Second harmonic. Right? Let's talk about third mode. So what happens in case of third mode of vibration? Okay, if pipe vibrates in third mode. So now this is an antinode, an antinode. Now what will happen? 3 nodes will get formed in between. Here 2 nodes got formed. Okay, so see, so again an antinode, antinode, then these are nodes, 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 and in between nodes there will be an antinode, antinode here. Okay, we can draw. So now what is the relation between length and the wavelength in third mode? So here L is equal to, you can say 3 lambda by 4. This is lambda by, sorry, 3 lambda by 2. This is lambda by 2. This is lambda by 2 and this is lambda by 2. Okay, so it is 3 lambda by 2. So L is equal to 3 times lambda 3 divided by 2. Okay, so therefore what will be lambda 3? Lambda 3 is equal to 2L upon 3. And again, if you take frequency, so frequency is, this will be N3, frequency of third mode. It is V upon lambda 3, and that's equal to V upon 2L divided by 3. So that 3 goes to the numerator. So it is 3 times V upon 2L. Or you can say it is equal to what? 3 times the frequency of fundamental mode. So N3 equals to 3 times N. Okay. So the case of pipe open at both ends, it is simpler. So here pth harmonic, sorry, pth mode is just pth harmonic, right? For open pipe, you have frequency of pth mode, Np is just p times the frequency of fundamental mode. Okay, and if you want to talk about overtone, so here pth overtone. Okay, so see, first overtone is frequency of second mode. Okay, how much is first overtone? It is 2 times n. Then next higher frequency is 3 times n. Okay, so that is, you can say, second overtone is 3 times n. Third overtone would be 4 times n. Okay, so pth overtone is equal to what? I'm writing p only for overtone also. Okay, but understand that it is p plus 1 times n, right? It is p plus 1 times n. Okay, and here if you see, all harmonics are present. You have fundamental frequency, then you have second mode in which the air column vibrates with 2 times of the fundamental frequency. The next mode, third mode, it vibrates with 3 times the fundamental frequency. So all multiples of fundamental frequency are present. Okay, all harmonics are present. So in case of vibration of in vibration of open pipe, all harmonics are present. Okay, so got it? Yes, no? Any question? So now, which pipe, open or close, has a richer set of frequencies? It is open pipe, right? So you make musical instruments using open pipe because more number of frequencies are present in case of open pipe. Okay, for an example, a flute. Okay, so flute, there are n number of holes on flute. Okay, so you lift one finger and this other end of the flute, it is open. Okay, so what would be vibrating length? So it is the distance between that open end, okay, and the finger that you lift. Okay, so distance between those two is the vibrating length, and that will determine the frequency that is produced when you blow an air through that flute. Got it? So if you go closer, if you go closer to that open end, okay, if you lift this finger, the frequency will be highest, right? That means, okay, what is frequency? It is V upon 2L. It's inversely proportional to L. Okay, so this is your open end, and suppose you lift this finger. So how much would be the vibrating length? It would be from here to here. Okay, so frequency is inversely proportional to vibrating length, right? Frequency is inversely proportional to vibrating length. So if you lift this finger which is farthest from the open end, the frequency of sound that is produced will be lowest. Okay, so as you go on lifting other fingers, right? If you lift this finger, frequency will increase. If you lift next finger, frequency will increase further. Okay, now let's discuss some problems based upon what we discussed today. So closed organ pipe closed at one end. Okay, there is clarification that it is closed at one end. Is excited to support the third overtone. It is excited to support third overtone. It is found that air in the pipe has. So for third overtone, okay, air in the pipe has three nodes and three antinodes, three nodes and four antinodes, four nodes and three antinodes, four nodes and four antinodes. What will happen? So this is third overtone. How much would be the frequency of third overtone? See, for fundamental mode, you will have a node, a node and an antinode. Okay, after that, first overtone will have one extra loop. Okay, so this is suppose first overtone, right? Second overtone will have one more extra loop. And third overtone will have one more extra loop. So how many nodes are there? One, two, three, four. Okay, how many antinodes are there? One, two, three, four. So four nodes, four antinodes. Get it? Next question. A cylindrical tube open at both ends has fundamental frequency F in air. The tube is dipped vertically in water so that half of half of it is in water. The fundamental frequency of air column is now. Okay. So you have this tube, right? Its length is L, suppose. Its length is L. Okay. So what is fundamental frequency of open pipe? It is VO. VO is equal to V upon, sorry, let's call it N, not V. NO, fundamental frequency, it is V upon 2L. Okay. Now what you are doing is you dip half of it in water. So half of it is dipped in water. So now how much is vibrating length? How much length is left for vibration of air column? It is L by 2, right? So let's suppose this is L dash, and now this has become a pipe open at one end. Okay, that is closed at one end, right? So now pipe which is closed, for that pipe, what would be the fundamental frequency of vibration? It is V upon 4L. Now the length has changed, so it is V upon 4L dash. Okay, and what is L dash? L dash is equal to L upon 2. So it is equal to V divided by 4 into L upon 2. This 2, and so 2 will be left there. It is V upon 2L. So it's equal to frequency of open pipe, right? It's equal to NO. Okay, so what's the answer? Option D is the answer. Very good. Option D is the answer. Okay, next question. The fundamental frequency of a closed organ pipe of length 20 centimeter is equal to second overtone of an organ pipe open at both ends. Okay, the length of organ pipe open at both ends is, so fundamental frequency of closed organ pipe. Okay, so NC is equal to V upon 4L, and NO is equal to V upon 2 times L, and this is some other organ pipe. Now you want NO second overtone. So what is second overtone? It is third harmonic, right? So NO3, this is O, okay, not 0. O3 is equal to what? It is 3 times V upon 2L dash. So it's given that fundamental frequency of closed pipe is equal to the second harmonic of an open pipe of some length. And question is, what is the length of the length of open pipe? Okay, so L dash is what we have to find out. So let's equate the two. So V upon 4L is equal to 3 times V upon 2L dash. So V gets cancelled. L dash is equal to what? 3 times 4L divided by 2. Okay, so it is 6 times L. Right? It is 6 times 20 centimeters. 120 centimeters is the answer. Option A. Right. Very good. So see, next question. An air column closed at one end and open at the other resonates with tuning fork when smallest length of column is 50 centimeters. The next larger length of column resonating with the same tuning fork is. Okay. So you have variable tuning fork. Sorry, variable air column. Air column of variable length. So its smallest length would be this much, right? It is V is equal to, sorry, L is equal to lambda by 4. Okay. So the next larger length of the column resonating with same tuning fork is. So what will be the larger length? So this is lambda by 4. This will be what? Lambda by 2. So it is 3 times lambda by 4. Okay, so L dash is equal to 3 times lambda by 4. And this is given that L is equal to 50 centimeter. So how much would be L dash? That means lambda by 4 is 50 centimeters. So L dash is equal to what? It is 3 times lambda by 4. That is 150 centimeters. So option A is the answer. Very simple, right? There was second NEET in 2016, and in second NEET also they asked question based upon this. The second overtone of an organ pipe has the same frequency as the first overtone of closed pipe, L meter long. Okay, so again, in both cases these are overtones and overtones. Okay, so second overtone of open pipe. So for open pipe, second overtone, second overtone. Okay, so N2 I will say it is equal to third harmonic, is equal to third harmonic, right? So N3 is equal to what? It is equal to 3 times the fundamental frequency, that is 3 times V upon 2L for open pipe. Okay. And this length we don't know. This length is what actually we have to find out. So suppose this is L dash. For closed pipe, for closed pipe, what is first overtone? So first overtone equals to third harmonic. Okay. Third harmonic, or you can say it is 3 times the fundamental frequency. Okay. So this is N3O we can say, or NO3, and this is supposed, sorry, NC3. Okay, C for closed. So how much is that? It is 3 times V upon 4L. Okay, so 3 times V upon 2L dash, NO3 is equal to NC3. Okay, so that is 3 times V upon 2L dash. L dash is length of the open pipe. It is equal to 3 times V upon 4L. So 3V gets cancelled. 2L dash is equal to 4L. That means L dash is equal to 2L. Option B. Next question. The two nearest harmonics of a tube closed at one end and open at other end are 220 Hz and 260 Hz. What is the fundamental frequency of the system? Okay, see, two nearest harmonics. What they mean to say is the harmonics that are present. Okay, nearest harmonics that are present. Okay, so if you take for an example, first mode or fundamental mode. Okay, the frequency is N, and then the next harmonic that is present in the system is, okay, next harmonic, okay, that is present in the system, that's present as frequency equal to what? 3 times N. So the two closest harmonics will have frequency difference of what? 3n minus 3n minus n, right? That's 2n. You can consider the next harmonic that is present in this system with the closed pipe. It is 5 times n. You can take difference between that next harmonic and this harmonic that's present. So it is 5n minus 3n, right? So that's 2n. So we can say difference between frequencies of frequencies of the closest harmonics, closest or nearest harmonics present in closed pipe is equal to 2 times n, right? So 2 times n is equal to, what is n? N is the frequency of fundamental mode. It is equal to 260 minus 220, 260 minus 220. Okay, so that's 40. So n is equal to 20, right? N is equal to 20 hertz. Fundamental frequency in an open organ pipe is equal to third harmonic of closed organ pipe. Okay, fundamental frequency of NO is equal to NC3, right? Third harmonic. The length of closed pipe is 20 centimeters. So this is 3 times V upon, sorry, it is closed pipe, V upon 4L. The length of open pipe is very straightforward. This is V upon 2L. Let's call it L dash. Okay. So VV gets cancelled. Okay, VV gets cancelled. And then you can say this thing gets cancelled, 4 gets cancelled. Sorry, the 2 will remain there. So 1 upon L dash. Take L dash on other side. So 1 by 2 is equal to 3 times L dash upon L. Sorry, it will be 1 here, right? Okay. So 3L dash equals to 2L. That means L dash equals to 2L divided by 3. So 20 times 20, 40 divided by 3 is how much? 10 point something, 13. Okay, 13 threes are 39, right? So 13 is the answer, option A. The tuning fork is used to produce resonance, resonance in a glass tube. The length of air column in this tube can be adjusted by variable piston. Okay, you can adjust the length. At room temperature of 27 degrees Celsius, two successive resonances are produced at 20 centimeter and 73 centimeter of column length. If the frequency of tuning fork is 320 Hz, the velocity of sound in air at 27 degrees Celsius is. Okay. So see, what is difference between the two successive lengths of a pipe which is closed at one end? Okay. What is the difference between lengths of two successive modes? For example, if you take first mode, length is equal to what? Length is equal to lambda by 4. For second mode, okay, let's call this L1, this is L2. Length is equal to 3 times lambda by 4. So these are successive modes, right? If you take next mode, it will be 5 lambda by 4. Okay. So how much is the difference? So L2 minus L1 is equal to what? It is equal to lambda by 2. Okay. It is equal to lambda by 2. So then from here you can find lambda, which will be 2 times L2 minus L1. That is 2 times of 73 minus 20. Okay, 53 times 2, 106, 106 centimeters, and V is equal to n times lambda. Okay, so it is 106 multiplied by 320. Okay, lambda is 106, n is 320 hertz. We want to find velocity of sound in air. So let's do this multiplication. It will be higher than 320. Okay, actually we have to do it. Okay, 320. This is centimeters. Okay, that is 1.06 in meters. So 320 times 1 is 320, and then you have 32 times 6. So 320 multiplied by 6. How much is that? 0, 6 threes are 18, 19. Okay, and 19.20. So 320 plus 19, 339, 339.2. Okay, so it's option B, 339, right? Meters per second. Option B. Got it? Yes, no? Okay, this is just calculation, right? Okay. Next question. A tuning fork with frequency 800 Hz produces resonance in the resonance column tube with upper end open and lower end closed by water surface. Okay, successive resonances are observed at length 9.75 centimeter, 31.25 centimeters, and 52.75 centimeters. The speed of sound in air is, again, very simple. Okay, so take difference between any two lengths, it should be equal to lambda by 2. Lambda by 2 is equal to L2 minus L1. So let's take this, L2 is this, L1 is this. So 52.75 minus 31.25. So how much is difference? 0.50, 20.50. Right, this is lambda by 2. That means lambda is equal to twice of this. So 41 centimeters is lambda. Okay, that means 0.41 meters. And then V is equal to n times lambda. So that is 800 hertz multiplied by lambda is 0.41 in meters. So 8 fours are 32. Okay, there is only one option, right? There is only one option. It is 344 centimeters. Option C. Okay. So is my calculation correct? Yes, no. This is 52 minus 31. Oh, this has to be 21, right? So this has to be 43. Okay, but since options are very well separated, okay, it's option C, 344 meters per second.